Hi everyone, I'm Sarah. I'm going to be talking about a tool that lets non-coders write programs in 5 minutes that the average CS PhD student can't write in an hour. And I'll talk a little about program synthesis, one of the key technologies that enabled that. But mostly I want to talk about what it takes to get to that point where your target audience can pick up and use your tool that easily. So we'll dive into the design process and some of the lessons the project taught us about making programming work for non-technical domain experts. Web automation is kind of an interesting domain. It's a domain where we've actually already seen 2 decades of end-user programming tools, but unfortunately none of them quite met user needs. So over the course of this talk, we're going to take a look at sort of that meandering path from when folks first started thinking about this issue to our recent tool that actually started meeting real users' needs. Now, normally this is the part in the talk where I would ask folks, have you ever written a web scraper? Now, I'm going to be watching this on Zoom when we're actually doing the sort of live version of this talk. So go ahead and react with the yes interaction on Zoom if you have, in fact, written a web scraper. Now, usually when I actually ask this question in live talks, you'll see that a lot of the audience actually has done this, which makes a lot of sense. There are a lot of people already today who realize the value of web data. It's really exciting to see that going forward, more and more people are realizing that. But the breakdown that I'm actually most interested in here is how sort of the population of folks who are interested is starting to change over time. So right now, basically, the folks who are getting access to web data are the folks who have the programming skills of probably the people who are watching this, people who could sit down and write a scraper with the tools that are out there today. But going forward, more and more folks from non-technical backgrounds are realizing the potential value of web data, realizing the things they can do with it. I'll give you a tour, an idea of why this is happening. So these are some of the things that our collaborators from the social sciences are doing with our tools right now. I'm just going to highlight one of them in particular. So these folks, they're a team from sociology, and what they're doing is they're using real-time data collected from Craigslist and apartments.com, and they're trying to figure out how should they set the thresholds for housing vouchers, the rent thresholds, in order to actually help low-income families move to high-opportunity neighborhoods. So that's the kind of question that folks are realizing they can answer based on having access to the right web data. But we didn't know that at the time that we started working on this. And so early on, we started working on this, and we reached out to a mailing list of a variety of different social sciences, and we asked, do you need web data? And we expected maybe we'd get a few responses, 2 or 3, giving us just an idea of the sort of stuff that they were looking for. And instead what happened was we realized that tons and tons of people were looking for this, and our inbox was flooded for the next 24 hours, and it was really hard to get anything else done. So we realized that data is out there. People definitely do want it. But at this point, with the tools they had available, they just couldn't get it on their own. Which makes a lot of sense. Web automation programming is really quite hard. So this comes from a user study that we did with, in this instance, CS PhD students. And we gave them a web automation task. And you can see that in the 60 minutes that we gave them, we had them time out after an hour. Only 4 out of the 15 were actually able to complete the task. But we can get everyone up to completing the task. And in fact, we can do it within 10 minutes if we just give them the right tooling. And so this was with our Helena tool that we ultimately built. And you can see that with that, the completion rate goes to 100% within 10 minutes. So there's a reason that it took those students so long to get things working, and why most of them ended up not being able to actually complete the task. So scraping is actually quite hard. We're going to do a little quiz right here. Feel free to answer these questions in the Zoom chat, or just think of them on your own. So here our goal is to scrape the product price over time. And basically what this little snippet of code is doing is it's going to actually go through all of the nodes in the page and give you back the node that has the text $26.06. So take a moment to think about why the snippet is not going to work. I'm going to give you the little spoiler there that the snippet is in fact not going to work. Okay, so I suspect some of you thought about the fact that basically what's happening here is the price might change, right? Once the price is no longer $26.06, all of a sudden that particular way of actually finding the data no longer makes any sense. And so what we actually need to do in order to make this a robust scraper, a scraper that's going to work over time as the price is changing, is we actually need to reverse engineer the page structure. We need to figure out, okay, we think this is going to be stable, we think this is going to be unstable, and so we'll only end up building our selectors for the data on the things that we can trust to remain the same. Okay, and so here's another snippet, which again, I'm going to tell you ahead of time, it's not actually going to work. So our goal here is to scrape the first entry in the Google autocomplete menu. And what we're going to do is we're going to put this query string into that text box that you see right there, and then we're going to go to the place where that first autocomplete entry should actually show up. So take a moment to think about why this might not work. Okay, so the reason this actually isn't going to work is that when you put that query string into the text box, that doesn't actually cause the autocomplete menu to be loaded. What's happening is underneath the service, there are all these JavaScript handlers that are waiting to run based on events being triggered. And so you typing into that box, lots of key downs, lots of key ups, that does cause the JavaScript handler to be triggered, but just pasting that query string into the text box does not cause it. And so if we really want our scripts to be robust, again, we have this reverse engineering task in front of us. We have to actually reverse engineer the JavaScript code that is running on the page. Okay, one last little quiz here. So if we are trying to click on product variant 2 and then click on add to cart, what's going to go wrong with this snippet? Here we just want to add that second variant into the cart. Okay, and I suspect some of you came up with it. Basically what's happening here is when we click on that product variant, the website is actually going to go back to the server and say, oh, give me the details for the second product variant. And so here in this script where we're not actually waiting for any time to pass, what's going to happen is we will click on the right button, it will go back to the server, but before the server can actually get back to us with the new information for that second product variant, we're going to be adding the cart, pressing the add to cart button, which is going to add the original product variant into our cart, which of course is not what we wanted. And for the human user actually using this page, this is all communicated visually, right? There's sort of a graying out. It suggests that you probably don't want to add to cart yet because something is happening. We're waiting for something to come back to us, but nothing actually prevents us from pressing the add to cart button. And so we actually can. And in this case, if we actually do with this snippet, we're going to get the wrong thing happening. And so this gives us one more reverse engineering task that we have to tackle, which is reverse engineering this communication with the servers or the AJAX that's running on the page. So basically, this is all very complicated, but if you're looking at this from the high level, you might be saying to yourself, okay, all that's happening is the user is doing some actions, mouse clicks, key presses, all those kinds of things, sending those to the browser, and the browser is sending back some data to the user. Let's just keep an eye on what the user does. Let's pop those recorded actions into an imitation user, and then let's actually use that to automate this task. And that's the core idea behind programming by demonstration, which is a particular class of program synthesis. So now we'll back up for a moment and talk about what program synthesis is. Basically, the idea is you have some kind of a specification, something probably other than code, although sometimes code is used, but usually it's non-code. That is the specification. The synthesizer takes that and then turns that into the program that actually fulfills the specification. Some of you may have heard of programming by example, where the idea is that the user gives some input-output examples, and that is the input to the PBE synthesizer, which then turns that into the program that you want, that turns each of those inputs into its respective output. In the case of programming by demonstration, we actually have even more information. So we both have these input-output pairs, and we have basically the sequence of actions that the user took in order to transform the input into the output. Now, web automation synthesis, and in particular web automation programming by demonstration, is a long-standing dream, ever since it made sense to talk about recent versions of Netscape Navigator and Windows 95. So way back in 1997, people started thinking that web automation might be a valuable thing to do. And sort of the first thing that they started thinking about was they were looking at these web pages and they were saying, oh, it kind of looks like there's a logical table here on this web page. Maybe we should extract that data. So that was sort of the first thing that happened. And then around 2001, web pages were starting to get a little more complicated, a little more interesting. People started thinking, well, maybe I actually want to test this web page. Maybe I want to automate interactions. And so they started doing web record and replay, especially for people who actually wanted to automate testing of their own websites. And then around 2009, well, we hadn't really made it to the point of actually synthesizing the programs that real users like those social scientists I mentioned earlier, the kinds of programs that those users needed. And the web had started getting much more interactive, which made the process of actually synthesizing programs much harder. And so at that point, with not having reached the kinds of programs that people actually needed, and now the challenge had actually increased, progress really stalled. So this brings us to our demo on how we actually unstalled it. So first, think to yourself for a moment, what data would you collect if you wanted to learn when CS researchers peak? Okay, I don't know about you, but for me, the first thing I think of is Google Scholar. And so I'm going to quickly walk us through how this demo is actually going to work before I actually show you sort of the video demo. So first up, the user is going to click on sort of the little icon that we use to indicate the browser extension. So the Helena tool is implemented in a browser extension. So first we're going to click on this icon. This will open up our control panel that we see over here on the left. But then we're just going to interact with normal web pages, basically to say, here is how I would find the information that I want to appear in the first row of each table that I'm interested in. So here, since we want to collect information about authors and papers, what we're going to do is collect information about the first author and the first paper by the first author. So here, let's go ahead and just give the demonstration of how to grab information about this first author. And then we'll do the same deal with the first paper by the first author. At this point, we can go ahead and say stop recording. The tool is actually going to write the program for us, and we can see the program actually presented to us over there in the control pane. And then at that point, once we actually press run, once we start the program running, we're going to see the preview of the data that it's actually collecting on the left, and on the right, we'll see the web pages that it's actually manipulating in order to get access to the data. And so here's how it actually looks when we're really doing it. So here we're going to give the demonstration of how we grab the information we want. Once we stop recording, the tool is analyzing the web pages. It has figured out how to add loops, and now we can actually run the program and start collecting the data that we want to collect. And so over there, we can see the data being accumulated. Okay, so that's how it all works. And I hope that after seeing that demonstration, you're thinking to yourself, end user program synthesis looks really cool. I bet users really, really love it. That's certainly what I expected based on sort of my early exposure to end user program synthesis tools and how easy they seemed to be. But in fact, the actual reactions that we've observed over the years are much more negative. In particular, we don't really have that many tools that users have actually adopted that have really made it into mainstream use, which basically means that we have learned a lot about what users don't like, but unfortunately not very much about what they do like. And that brings us to this talk and really walking through, okay, what does it take to make a tool that the users will actually like, that they will actually use and adopt? So I want to talk a bit about some of the things we had noticed in the history of programming by demonstration broadly, but especially programming by demonstration for web automation. And so this is a quote from a beautiful paper by Tessa Lau, which is basically talking about when a user has given 5 very repetitive demonstrations, and then they have to give a 6th repetitive demonstration in order to fix something that they perceive as very simple, as just a tweak, something that they could really naturally express. It's very frustrating to them to not be able to just express that in the simple way, but instead to have to give another repetitive demonstration. And then here's from another paper, which is observing that if they had to give multiple different kinds of demonstrations to complete different parts of the program, that was very confusing for users, made it very overly complicated. And then we have sort of the one main success story from program synthesis, which is Excel's flash fill. And so this was a tool that actually was adopted into Excel, but over the course of putting it into Excel, they actually had to study, okay, what will it take to make users actually like this feature? And the main thing they discovered was that if the user gets the right program after giving exactly one example, the user's happy. If they do not get the right program after just one example, they're not. So let's actually diagnose. What's sort of the running thread through all of these? So this was being frustrated about having to give multiple repetitive demonstrations. This was all about being confused by having to give multiple different kinds of demonstrations. This was about only being happy if they got the right answer based on one example. And so if you look at the common thread through this, it's about single demonstration. You only get one example. And that led our project to ask, could we do programming by demonstration with one demonstration? Now, if you're a synthesis person, your natural instinct at this point is to say, no, you absolutely cannot do that, because that is a very, very ambiguous specification. And that's true. Say we give the demonstration with the paper highlighted here in orange on the left. That could be consistent with many different programs. Do we want to make the program that collects the first paper by each author? All papers by all authors? All papers with more than X citations? All papers that mention the word learning in the title? The demonstration that we actually gave is consistent with all of those different programs. And so how will we actually disambiguate? This brings us to the core insight that drove the approach we ultimately ended up taking. So what we figured out was that for this audience, drafting programs is hard. So they have blank page syndrome. They're sitting there looking at the blank editor window, and that is extremely intimidating. A lot of these folks, they've actually been trained in programming, usually a couple semesters, especially for data analysis. And even in those domains where they've actually been trained, they very, very rarely start from the blank editor window. What they do is they take a program they've used in the past, whether it's for a prior project, whether it's from a particular course, they'll take that existing program and then they'll tweak it until it works for their current needs. So the observation here is that drafting programs is very hard, but editing is easy. And in fact, this already came up a bit in one of those quotes that we pulled out earlier. So in particular here, the users were saying that they wanted to be able to directly modify the generated hypotheses. They wanted to say, no, 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 just do this. Let me just edit the program that you're actually producing. So this is something that users can do, and they want to do it. So this is how we ended up reshaping traditional programming by demonstration into a new form. So in traditional programming by demonstration, you have a lot of different demonstrations. You throw those all into the synthesis algorithm. The synthesis algorithm produces a program. The program, once you run it, produces an output. The user looks at that output in order to actually debug the program. So they say, is this output what I actually expected? Because they are not expected to actually read and understand the program. They're expected to read and understand the output of the program. If they like the output, fantastic, they're done. If they don't like the output, they have to go right back around this loop, so they give another demonstration and they keep going. In our approach, demonstrate once, revise any time, sort of the DORA workflow, it's very different. So instead, the user gives a single demonstration. The synthesis algorithm pops out a program. It may not be the final program, but it is a draft program, something that is going to get the user close to what they want. And it is expressed in a readable or learnable language so that the user can then directly edit. And so this gets to the two main things that we actually needed based on the user feedback. So the fact that it needs to be a single demonstration and the fact that it needs to be an editable program, something that the user can directly manipulate. I want to briefly talk about why one demonstration really is 10 times better than 2 demonstrations. So we already talked about the fact that it makes users happy and successful. So that's a key part of it. But it's also really interesting in terms of how it changes sort of our role as the synthesis designers. So all of a sudden it's okay if the synthesizer that we're building can't reach every point in the space, as long as they can get to something that's close to what the user needs. And so that actually dramatically eases the role of the synthesizer. That makes it much easier to build a synthesizer that's going to do the job. It also changes sort of the supporting infrastructure that we end up needing to build. So we don't have to add this ambiguity detection layer or the interface that is actually going to solicit disambiguating demonstrations. The other key thing is that it actually changes the class of programs that we can tackle. So in the past, we really expected that the user was not going to be able to read the program, but was going to be able to read the program output. That is actually quite limiting for us. If the user is trying to create programs that would run for hours or even days, we really can't expect them to debug that by looking at the output because the debug loop would be so long. The other key issue there is if it's an output that's very large. Again, that's something that we really wouldn't expect the user to inspect because that's just going to be too much for them to tackle. And so all of a sudden, by shifting from debugging by looking at the output to debugging by looking at the program, we can start tackling a much broader class of programs. And that's going to be important for something like web automation, where these are really long-running programs that produce really large data sets. And we really don't want the user to have to be debugging by looking at the output. Okay, so we talked about the fact that this basically lets us do single demonstration and editable programs, the two main things that users ended up needing. But this is going to break down into 2 key things that we'll have to build for them. So the single demonstration, that's going to come down to building usable drafting tools. And then making sure that users can actually directly edit the programs, that's going to be all about giving them learnable languages. And we're going to talk about both of these. And naturally, both of these are also usable outside of DORA workflows. So this isn't to say that these are only useful inside a DORA workflow. Now, this was a long-running project that had a lot of different sub-goals and many different parts over the course of the years. I'm going to focus on just a couple of the key goals, the ones that relate to the kinds of things that we're talking about today. So in particular, how we can synthesize complex programs from a single demonstration. So how can we get them that first draft of the program that they're going to then edit? And then goal 3 here is making programs robust and human readable. So what is it going to take to make sure that those programs that they're seeing are programs that they can actually look at, understand, tweak? So we heard a few things from our users about what they actually need. So first and foremost, multi-load data. This isn't just I come to page A, I grab the data that is available on page A. This is instead data that is spread over thousands, hundreds of thousands of pages. They're accessing it via all the same things that you or I would do as we are browsing the web. So they're clicking, they're entering data into forms, they're typing, they're interacting with little calendar widgets, all the same things that we would do, they would do. And the other key thing is that they are getting hierarchical data. They're looking to get tree-structured output data. So they're not just looking for a table of authors. They're looking for a table of authors and a table of papers, and they need to maintain the links between those tables. So let's talk about why this is so hard. Basically, if we're collecting tree-structured data, naturally we're going to end up needing nested loops to do it. Now, if you're a synthesis person, this is a point where you are getting very nervous, because if you have a space that's just all the programs with no loops, honestly, that's already a pretty big space, but let's say that that's manageable. Now let's add programs with one loop. Well, now this is getting to be actually a really large space. And if we're starting to allow multiple loops, well, that's a massive space. How are we going to search that whole space of allowable programs? And so at this point, we hit a fork in the road. How should we synthesize these programs with nested loops? What are our options here? So usually what you do at this point is you say, okay, I've just got to drill down, make a smarter, faster synthesizer. Well, we started asking ourselves, is there some other way? And this led us to thinking about the class of demonstrations we were allowing users to give. So demo 2 over here on the right, that's the same one that you saw during the video demonstration. Demo 1, we're playing around with some papers, we're pressing the back button, we're getting to one of the authors. Both of these would be perfectly reasonable ways to express the problem to a human, to teach them how to collect the data. But one of these is going to be a lot easier for a synthesizer. And so in particular, if we allow both of these demonstrations, we really can't do anything better than just searching the space of all Helena programs until one of them is producing the data we want. But if we limited it to the demonstration on the right, we could do something a little smarter. So basically, in the space of possible demonstrations, there are going to be some things that are synthesizer friendly. And for those, we already know how to write a synthesizer that is going to produce the set of output programs that we want from a particular class of synthesizer friendly demonstrations. And for anything outside of that space, we just don't know how to write the synthesizer or the compiler that converts those demonstrations into the output programs we want. But we've seen what happens if we push too far on making something synthesizer friendly, right? So we could go all the way to the point of asking users to provide 1,000 highly repetitive demonstrations, and that's not going to make for a good tool. And so we need something that's both going to be friendly to the synthesizer and is actually going to be user friendly. We need something that falls at that intersection and works for both human and machine. And this led us to the particular balance that we found for this tool, which was making a contract with the user. In particular, now this isn't how we would express it to the users, but basically what we require them to do is demonstrate the first iteration of each loop, ordered from outer to inner loop. And we're helped in the second one by the fact that the way you navigate the web actually enforces that second one. So this dramatically simplifies the process because all of a sudden that demonstration on the left, that one's out. The user is not allowed to provide that. And all we have to do for something like the demonstration here on the right is just figure out where to insert loops and over what. And that's a much simpler problem. So let's start with the assumption that we actually know what tables are interesting to the user. That's a big assumption, but we'll leave that aside for now. That means that we can go ahead and label all of the actions the user took according to whether they used any of the tables of interest. Then we can go ahead and actually add in a loop before the first use of any of a table's cells, ending after the last use. And so you can see how that works out for these particular tables. Now, we do actually have to find those tables. We're not going to run through the actual approach that we use for that, but I'm going to give you an idea of the intuition by basically giving you another one of these pop quizzes. So, taking a look at this page with this set of papers by the author, we see a number of interacted nodes highlighted in red. Do you think that there are any other rows that have the same logical structure on this web page? Okay, so I'm assuming that you looked at this page and you thought about it and you said, yes, it looks like there are other papers on this page. That's certainly what I would think. What about here on this Craigslist page? Are there other items on the same page, other rows of a table that have the same structure? My impulse looking at this and having interacted with many Craigslist pages is no, there's no other listings on this page. This is sort of the details page for a single listing. What about over here on Twitter? Yeah, so notice that there are these sort of multiple kinds of data that are actually highlighted in red on this one, right? So we see that Gates Foundation over there on the left, but then we also see the particular tweet data over here on the right, sort of in the center. And so this gets a little more complicated, right? It seems like probably a subset of the interacted nodes are actually part of a table. So it looks like there are multiple tweets on this page, but that maybe those other two highlighted ones are actually not part of the table that we're seeing on the page. And so basically this exact same intuition that you're using when you're looking at these pages is also what our tool ends up using. So basically we can take advantage of the fact that there are best practices for how you display data on the web, and data that is logically structured similarly should also be physically structured similarly on the web page. And so that's the basic idea of how we can actually figure this out when we're seeing new pages. And so this has dramatically simplified the process both for the machine and for the human. So for the machine, we've gone from having to search the space of all programs in the Helena language to this much more constrained problem of how to synthesize a table selector from looking at a page and having just seen the interacted nodes. Still a complicated problem, but much simpler than the process of actually searching all possible Helena programs. And then for the human user, in comparison to using traditional web scraping tools where they would have to reverse engineer the web page, all they're being asked to do here is actually learn a demonstration contract. So that's a much simpler ask. And indeed, users do perceive Helena as more usable. And in fact, what's most interesting to us, and I'm going to get back to this message later, this key idea, is that users perceive Helena as much more learnable. You can see there how big the gap is from the traditional web automation tool. So are users more successful with Helena? Here we're seeing how long it takes them to actually solve a particular web automation task. And I want to emphasize that these times actually do include training time. So when you see the sort of the users, each user ticking up on that purple line, that's going from 0 is I've never heard of Helena before to when that little tick goes up is when they've actually completed their first web automation task with Helena. Okay, this brings us to how can we make programs both robust and human readable? We talked about usable drafting tools. Let's go ahead and move on to learnable languages. And remember, these map cleanly onto the two things that our users said they needed, so single demonstration and editable programs. Let's talk briefly about why learnable languages. So one reason is you might be in a DORA workflow where you're asking for a quite ambiguous specification from the user and you actually need them to go in and resolve the ambiguities by directly editing the program, which of course naturally means that the user has to understand the program. But you might actually want this for any synthesis-based drafting tool. So if you want your user to trust the programs that you're actually producing, it really, really helps if you have a readable representation of what the synthesizer produces. And so here we're going from the case where we can only ask users to examine small outputs that are created very quickly, to all of a sudden it's okay if the program produces a large output because we're not actually asking the user to look at the output in order to do the debugging. Instead, we can actually have them directly look at the synthesized program because, again, the program is expressed in a readable, learnable language that the human user can actually understand, even with limited background. And again, so this is especially important for long-running, large output tasks or for tasks that are high stakes, and so user trust is very important. But how can we actually do this? So this is a really interesting class of users, right? These are folks who really haven't had a lot of exposure to programming. They've maybe had 1 or 2 semesters of training in data analysis programming, usually in R or in Python, or depending on the field. So I've worked with folks from a variety of different social sciences. It might be Stata or SPSS. And they may need web automation maybe 1 or 3 times a year. Some of them need it more, but this isn't necessarily a frequent need. And if it's not a frequent need for any particular individual, we shouldn't necessarily expect that they're going to retain the language between uses. And so this leads me to drawing a particular distinction that I suspect many folks have already thought about. But that's the difference between learnability and usability. So usability, that's going to be about whether you're an expert or a non-expert, how easy it is to use the language. But learnability is specifically putting the focus on how long does it take, how hard is it for users to get from really not being used to the language, being accustomed to the language, to comfortable using it, can actually do the tasks they need to do. And so for these folks who are using this particular language, using this particular tool 1 or 3 times a year, these folks may never even want to become experts. And so for them, it's really all about learnability, and they're not that interested in how usable a language is for an expert. They're interested in how long is it going to take them to get from not remembering the language to actually being able to use it for their particular tasks. And so I highlighted the fact that these times that I reported in that user study that they actually include training time. This really is the important metric for these particular users. What we really want to see is how long does it take from either having never used the tool before or not having used it for a year, having forgotten all of the details, to having actually completed their tasks. So this really is the metric that we're interested in here. And this brings us to block-based programming to the rescue. Given that we don't want these users to have to take a class to learn how to use this tool, and we don't want them to spend a day relearning it every time they need to use this tool, we want something that they can just pick up and use. And it's not that what the user is doing here with these blocks is so complicated. They could absolutely memorize this language and use it in a text-based programming environment, but why make them remember its ins and outs when we can take advantage of recognition over recall, when we can put all the pieces they need at their fingertips in a blocks-based environment? For them, this is an infrequent need, an occasional task. They're not looking to become expert scrapers, to be the masters of this domain and this language. They're looking to get their tasks done quickly so they can get the data they need and do their real work. Now, there was one more challenge to actually delivering this vision to them, which is that what the web browser sees internally when the user does a variety of actions, whether that's mouse clicks or typing, is a lot of really low-level DOM events. And so here we're seeing just tiny little slivers of what happens when you do 1 click or you start typing 1 word. And all of the stuff is pretty ugly, and you wouldn't even want to show it to an expert programmer. You certainly don't want to show it to a non-expert programmer. What we really want to show the user, of course, is this high-level language. And here you can see we've highlighted that this is the actual Helena language. And so what do? If we need this low-level language for robust replay, and we do, we talked earlier about the fact that all those JavaScript handlers that we were going to have to reverse engineer were being triggered by all of these low-level DOM events. If we need this low-level language for robust replay, but we want to show the high-level language in order to actually make something readable for the user, what do? What should we sacrifice here, robustness or readability? Feel free to type your answer in the Zoom right now. And so, of course, naturally, it's neither, right? So we can show the users the high-level view while still maintaining the low-level information beneath. And so that's what we actually ended up doing for the Helena project. So we have these web interacting statements where over the course of the recording, when we're actually watching what the user is doing, we're seeing what comes in the low-level language. We're seeing in DSL2. We'll then use a reverse compiler to map it into the high-level language, which we can then display in our blocks-based editor. And then based on the custom program editor that we have produced, all the changes that they're making can be mapped back down into the low-level language, which we actually need in order to do the replay on the web pages. And of course, some of our interactive statements are not actually interacting with the web, and so we don't actually need to map those back down. And so this lets us synthesize these huge but still ultimately editable programs. And so this is really exciting, right? Because you might think to yourself, oh, if I need to have low-level code, if this is a domain that is abstraction resistant, then can I even use one of these high-level languages? Can I use something that would be suitable for a blocks-based editor? And the fact that we need low-level programs, the fact that we're tackling domains that resist clean abstractions, even the fact that we're dealing with these very large programs, these low-level DOM events, there are going to be hundreds, even thousands in a single script. But none of these actually prevent us from using these block-based programming environments. So that's really exciting for us, the fact that we were able to make it work, even despite sort of these barriers to using these highly learnable languages and highly learnable programming environments. Okay, this brings us to the future of usable programming. We've been working with social scientists from a variety of different domains, and it's become clear increasingly more every day that novice coders and non-coders have so many diverse programming needs. They want to tackle all of these different domains, and they have all these different things that they can tell us in order to actually draft these programs in the first place, which is really, really exciting based on the fact that we have all of this information, all of these different ways that they can express their intent, which they could use in the context of a usable program drafting tool. All we need in order to actually put these domains in reach for them is to actually produce the learnable languages for these domains, to take advantage of the information that they're already comfortable communicating, and then actually put the languages, the programs in reach for them via learnable languages. I think this is really important going forward because I talked about how the audience of people who's interested in web data, how that's been changing. But I think this is a much, much broader trend. It's not just about web data, it's about programming languages and tools much more broadly. So going forward, only a teeny tiny slice of the people who are out in the world writing programs are going to be people who have had the kinds of computer science training that programmers today have had. So many different people from different backgrounds end up wanting to get access to the power of automation. And I think Snap can really help us here, can really help us serve these users. It lets us put these complicated programming tasks in reach for new audiences. And with that, I would love to take any questions, either about the Helena tool in particular or about the future of usable programming and how we can bridge programming languages and human-computer interaction to actually develop that vision, to actually deliver programming tools to new audiences.